Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi everyone, welcome, thanks for coming. We're happy to have Yuval Perez talk today about random walks on groups and the Kaimanovich-Vershik conjecture for Lamplighter groups.
Thank you. So this work arose from writing the relevant chapter in the book with Russ Lyons on random walks or probability on trees and networks more generally. And this is the section, we were getting to the section on random walks on groups, and one of the well-known conjectures is in that area is due to Kaimanovich-Vershik from '83. So I want to tell you the history of that conjecture, and as we were writing the section, we realized we actually know how to solve that question. So I also want to tell you the solution, which is a nice application of entropy. Let's see, is this working? Okay, so but the main purpose is to use this an opportunity to share what I think is really a beautiful area, random walks on groups. So as I mentioned, what I'm talking today is joined with Russ Lyons. Now, if I'm going to be writing on the board, so people, if you could move forward, you would see much better. So I would suggest, because there's no slides. So this is joined with Russ Lyons. So the basic setting is we have a group G, which is finitely generated by some set of generators S. For the purpose of this talk, really three types of group will be enough. Just the usual lattice ZD, free groups or trees, and the Lamplighter groups. But there is a much more general theory. So we have group S is a finite set of generators, and it's symmetric. Okay, and there is a usual Cayley graph. So X is a neighbor of Y if and only if X is in Y times the S. So this is the right Cayley graph. We'll be interested in the simple random walk on this Cayley graph, and it's often convenient to avoid periodicity issues and talk about the lazy simple random walk, where Pxy is just a half if X equals Y, and 1 over twice the size of S if X is a neighbor of Y, and 0 otherwise. But this transition matrix is just the average of the transition matrix for simple random walk and the identity. So the basic questions, there are many questions. The basic questions involve the asymptotics of the random walk. So one particular asymptotic is the asymptotic distance or the speed. So we're going to write rho for the graph distance, and if E is the identity, then the distance from E to X will sometimes just abbreviate as the absolute value of X. So this is just the length of X, the length of X when you write it in a word in the generators. It's the shortest word that represents S. And then the speed of the random walk is just the limit of the expectation of xn divided by n. And the reason this limit exists is because, if you just write down the triangle inequality, so the distance from this to the identity is at most the distance from E to xn plus the distance from xn to xn plus m. And now you just take expectations and use a group invariance, so you have expectation xn plus m is less than expectation xn plus, and this is, expectation here is the same as that. So you have subadditivity, which then implies that this limit exists. In fact, a subadditivity actually implies, we won't need this, but this equals the almost sure limit of xn over n. So you don't need to take expectation because of the Kingman subadditive ergodic theorem. But the elementary definition is with expectation, and then just use the fact about subadditive sequences of numbers that when you divide by n, this limit exists. So one basic question is, when is this speed positive? So let's recall the basic example. So of course, for a random walk on the usual lattices ZD, the speed is 0. If you have a tree, which is a Cayley graph, so this is a Cayley graph of a free group, a free product of 3 generators, or you could take 4 regular tree, which is the usual free group. Anyway, on this tree, if you look at the random walk, if this is, say, the identity, then of course the walk is transient, and at every vertex with probability 2/3, we move further from the root. With probability 1/3, we move closer after we left the root. So the speed, so here the speed is 1/3, or in general, it will be d minus 2 over the degree, right? So if you have a d regular tree, there are d minus 1 edges going further and 1 edge going back. So you'll get d minus 2 over d for the speed. So that's just elementary from the usual law of large numbers. So let's come to our third example, the Lamplighter groups. So on the Lamplighter group, rather than draw the Cayley graph, let me draw one element of the group. So one vertex in the Cayley graph, and then just tell you which are the neighbors of this vertex. That's all we need to understand the random walk. One can describe the group operation, but it was not really needed. So here is an element of the group. It's given by a finite sequence of lamps, some of which are, so now I'm talking about the Lamplighter groups. And I'm starting with the one-dimensional one, which is called G1. So this is a Lamplighter group just over Z. So we have a finite collection of lamps that are on, and then all the lamps are off, except for finitely many. And we also have a marker, or a lamplighter, just draw an arrow, which think of it the location of the current location of the lamplighter. So this is just one vertex in the group. It's given by the location of this arrow, which is an integer, and a finite set of the integers, which are where the lamps are on. Okay? Now, what are the neighbors of this configuration? One neighbor is obtained by flipping the lamp where the marker is. So this 0 could be changed to a 1, so this lamp could be turned on. Or if the lamplighter was in a place where the lamp is on, he could flip it off. So that would be one neighbor. And then the other neighbors are obtained by moving the marker either right or left. And we could do this on any base graph. So if we have the base graph is the two-dimensional lattice Z2, then we would construct the Lamplighter group G2, where again we have finite collection of lamps that are on. Maybe I'll draw them in red. So these are on lamps, and then all the other lamps are off. And we also have a marker which is in some lattice location, say in this lattice location. Okay, and again, the legal moves are we could flip the lamp where the marker is, or move the marker to one of the lattice neighbors. So here in G2, the degree is 5. Okay, and similarly, one can define the groups GD. Now, all these groups have exponential growth. So when we measure the growth of a group, we look at the ball of radius r and ask how many points are in there. Does it grow polynomially, exponentially? So of course, in the lattice ZD, it grows like a radius to the d. In the tree, of course, it grows exponentially. What about here? It's also exponential. So we can easily see that within distance r from, so the identity of the group, I didn't tell you what that is. That is just when the marker is at the origin and all the lamps are off. That's the identity. And within distance r of the identity, you certainly have more than 2 to the r over 2 configurations, because you can just go to the right distance r over 2 and turn on any subset of the lamps, and that will take you less than r steps. If you do this more carefully, you get the Fibonacci recursion. So it turns out the actual, if you take the size of the ball of radius r in G1, then it asymptotically, the size of it grows like the golden, the golden mean to the r, well, up to constants. So I'll write just theta here. But that's not important here. It's just easy to see that there is exponential growth here. And of course, in all these groups, there is exponential growth. And so naively, we would think that the difference in speed here arises from the fact that here it's polynomial growth, here it's exponential growth. But the Lamplighter groups are, a sobering example. So if you look at G1, then clearly the speed is 0, because by time n, the Lamplighter the marker itself is just going, doing a delayed simple random walk. So it will go distance about root n. And all the lamps that are on will be in that subset that he's visited. So the distance from the origin will grow about root n, certainly less than root n log n. So it's going to be, the speed will be 0. In 2 dimensions, it's also true that the speed is 0. And basically, it's due to the recurrence of the simple random walk in the plane in Z2. And that recurrence implies that if you look at the range of the simple random walk in Z2, so how many vertices has the marker visited, that's going to grow sublinearly. In fact, we know exactly it grows like n over log n. So the lamps that are on will be only on some connected subset of size n over log n. At any time, that connected subset, there is a spanning tree there, and you can just, at any time, go back to the identity by going along this spanning tree and turning off the lamps as you go. So the distance from the origin is going to grow sublinearly, just barely. Once we go to 3 dimensions and higher, then the speed is positive, because the random walk on the base graph on the three-dimensional lattice is transient. So it is moving at 0 speed, but it's transient, which means the range of the walk is going to be linear in time. Transience implies that every vertex is visited in expectation a finite number of times. So by time n, you will visit order n different vertices. Each visit you vertex, with constant probability, you turn the lamp on before you left there. So it's easy to see that the number of lamps that will have been turned on is linear in n by time n. So the speed there is positive. So see that exponential growth doesn't determine. When we go, G1 has speed 0, G3 has positive speed. Both of these groups actually are amenable. which means the surface to volume ratio goes to 0, so that doesn't determine things either. So what does determine things is something else which in general determines the asymptotics of the walk, which are harmonic functions. So harmonic function on the group is just satisfying u of x is the average over the neighbors of u of y. Okay, which can be expressed as saying that if we take the matrix of simple random walk and multiply it by u, so think of the function, so u is a function on the group, but we can think of it as a column vector. We multiply by the transition matrix, and this should be just identically u. And it's the same as saying that if I take p, which I define to be this average, then I'm saying pu equals u. Of course, these equations are equivalent because of this. Okay, so these are harmonic functions, and harmonic functions are really key to understanding asymptotics of the walk. So it turns out that on these examples, all bounded harmonic functions are constant, and on this they're not, and that's part of a general equivalence. So to see the importance of harmonic functions for asymptotic, I want to define the tail sigma algebra of the walk is defined as whatever you can see when you only see the far future of the walk. So formally, we intersect over all n the sigma field determined by xn, xn plus 1, and so on. So this is so formally you could think of any event where the indicator of the event can be written as a function of the variables from time n on, and that's true for every n. So example of a tail event will be, is the speed taking some value? But because the speed is going to be almost sure constant, that's not going to be very interesting events. On the tree, we have natural tail events. The random walk on the tree is going to be transient, so it will go off to infinity. And we can ask, does it go off in this part of the tree? That is, right? So this edge determines a partition of the tree. And we can ask, does the random walk go to infinity on this part of the tree? And that's a function. So if you have the probability starting from x that the random walk ends up in somehow this part of the tree, I'll just write left part of tree, I'll be more formal in a minute, then this is a harmonic function of the starting point, because to determine this, you just have to, so it's easy to see, it must satisfy this identity just by conditioning on the first step of the walk. So, and this function is an interesting non-constant function, because if x is already deep in this part of the tree, say here, then this function is very close to 1, because the walk is likely to end up here. It's not too likely to come back to this edge at all. While if so this was the key edge that was separating things. While if x is here, then the walk is unlikely to end up on this side, on the left side of the tree here, because it would have to go and reach this edge, cross it, and never come back. So it's easy to see that u of x is not a constant. And this is part of a general connection. So for any tail function, so a tail function is, so it's a function of the path. Okay, but it's a tail function. Formally, it means it's measurable with respect to this tail sigma field, or equivalently, it just doesn't change if you change the first few steps of the path. And so for any tail function, you can define uf of x to be the expectation starting from x of f. So we start a random walk at x. Okay, and now I claim that this function is always harmonic, and this is easy in the for lazy random walk. It's true for any random walk in the group. So this is harmonic for random walks on groups, and also for any lazy Markov chain. But not for any Markov chain. You need some condition, but if it's a group, it's fine. If it's lazy, it's fine. And here I'm going to make my life simple by just assuming that you have a lazy walk on a group. And the reason it's true is because...
Maybe you want the mic go off.
This is tough. I don't know how to... Thanks. Thank you. And the key is that, so let me explain this for a lazy walk. And the key is for a lazy walk, we can write if yn is a simple random walk, then, and xn is the lazy walk, then we can write xn as y at a binomial time, binomial n-half. Right? Because we can obtain the lazy walk by just tossing a fair coin to decide if we're moving or not. And so the number of actual steps performed by the simple random walk by time n will be a binomial n1/2. And then the fact that a binomial n1/2 is very close to binomial n+1/2 in total variation, which it's just a simple calculation that I distributed in the notes. So this total variation goes to 0, means that we can define another copy of the walk. I'll write x0 tilde. So we start at x. And we can couple the two walks so that, so this is the lazy walk. Another copy. It's not an independent copy. It can be coupled so that xn tilde equals xn+1 eventually. Okay, so when you run these two walks, they start with a shift of 1, but the fact that this total variation distance goes to 0 implies that you can do this coupling. And then the way we use it is to check harmonicity, we apply p to uf of x. Now, by definition of p, it's just moving time one step forward. So this is the expectation starting from x. So starting from x means x0 is x. And then we look at f of x1, x2, x3, and so on. But because of this coupling, this is called the shift coupling. This is the same as the expectation of f of x0 tilde, x1 tilde, and so on. So this is another sequence which, because the sequence eventually agrees with x1, x2, and f is a tail function, then these two things are just equal. But now this was our definition of uf of x. OK, so there's a correspondence going from tail functions to harmonic functions. And this is invertible because given any harmonic, and I'm going to now focus on, so I'm going to focus on bounded functions. So observe that if f is bounded, then uf is also bounded. And given a harmonic bounded function, given a harmonic bounded function u, can define the corresponding f of x0, x1, x2. Well, I want to define it just as the limit of u. Let me write as a lim sup just so it's defined everywhere. So the lim sup of u of xn. So with this definition, clearly is a tail function. And if I take this function f and apply uf, so I have to, so uf of x is ex of the lim sup of u of xn. And now the key is u of xn is a martingale. So for function xn which is harmonic, that just means that u of xn will be a martingale, and it's a bounded martingale. So so this, with probability 1, this lim sup is the limit, and the expectation stays the same for a martingale. So this expectation will just be equal to u of x. So there is a one-to-one correspondence between tails functions and on the sequence space and harmonic functions on the group. So this really means harmonic functions are describing the asymptotic behavior of the walk. And the important thing for us is that you easily immediately get from this that the tail is trivial, which just means that for any set A in the tail, the probability starting from a point x of A is either 0 or 1, if and only if all bounded harmonic functions are constant. So that's an easy consequence just of this correspondence if we let f be, if there was a non-trivial event A, we could define a harmonic function which is we take f to be the indicator of A, we could define that corresponding harmonic function, and that function would be non-constant. Okay, so that's the basic correspondence. And okay, and now key theorem, going back to Kaimanovich-Vershik 83 and Varopoulos 85, is that the following three things are equivalent. One is that the speed of the walk is positive. Two is that there are bounded non-constant harmonic functions. And three is that the entropy of the walk is positive. So I'll say what that is. The entropy, call it h, is the limit of h of xn over n. So the entropy of a random variable, it's just the entropy of its probability distribution. This random variable takes finitely many values. I recall the definition of entropy in the handout. And again, there is a subadditivity. So the entropy of x n plus m is less than the entropy of the pair xn and xn plus m, which is less than the entropy of xn plus the conditional entropy, it's equal to the entropy of xn plus the conditional entropy, and the conditional one is just, in fact, here there is an equality, because once you condition on xn, then the distribution of xn plus m is just like the original distribution of xm. So you get, this is the basic inequality on conditional entropy. Again, I recalled it there. So so you have again subadditivity, so this limit exists, and the equivalence is that the entropy is positive. Okay, so these three things are equivalent, which is a very powerful result again. So the equivalence of 2 and 3 were proved by Kaimanovich-Vershik. Varopoulos added the equivalence to the speed. So let me quickly indicate where these are coming from. So let's write h of, so I'm going to start with the equivalence of 2 and 3. So let's write xk given xn plus h of xn. This equals h of the entropy of the pair, xk, xn. And we also want to write it the other way. So it equals h of xk plus the entropy of xn given xk. And observe that, as we already said, this is the same as the entropy of x n minus k. So first, let's use this. So we're going to use it a couple of times. Okay, maybe let's rewrite. So hxk given xn equals h of xk plus h of xn minus k minus the entropy of xn. And just for the case of 1, I want to emphasize this. So this is h of x1 plus h of xn minus 1 minus h of xn. Now this is decreasing, because when we have a Markov chain, the entropy of xn1 given xn is the same as the entropy of x1. I'm sorry, it's increasing, because same as the entropy of x1 given the whole tail from xn. Because if I know xn, the future is not relevant to determine x1. But this is a decreasing sequence of sigma fields. So if I condition on less and less information, the entropy of x1 grows. So this is increasing in n. So this is increasing, which means, right, so this is not changing. So it means this is increasing. So it means the marginal h of xn minus h of xn minus 1 must be decreasing. Now what will be the limit? The limit must be exactly this h, because once we know this is convergent, this is just a Cesaro average of these, so it must converge to the same limit. Okay, so the limit is exactly h. Now, on the other hand, so this tells us this goes to h of x1 minus h. But this converges to h of x1 given the tail. Okay, now we're in set to prove the equivalence of 2 and 3. So if so let's do the. So if the entropy is 0, so this is, I guess 2 implies 3, because if the entropy is 0, let's see, which direction do I want? No, actually, let's start with 3 implies 2. So again, we know that this expression here, h of right, so h of x1 given tail equals h of x1 minus h. So if h is positive, then conditioning on the tail matters. So the tail is non-trivial, because conditioning on something trivial won't change anything. Now if h equals 0, then we can use the same thing for k. Then we can write h of xk given the tail. The same, if you just use that identity there, you get that's h of xk minus kh. So if h equals 0, h of xk given tail is just h of xk. So it means that the tail is independent of x1, x2, up to xk for every k. But if the tail is independent of all of these, well, it's independent of what they generate, so it's independent of itself, so the tail must be trivial. Okay, so that's the equivalence of 2 and 3. And quickly explain 1 and 3. So all right, so let's write. So this is no good. Non-trivial. Okay, so let's write the entropy of xn. So I'm abbreviating Pn from the identity to x. I'm just writing Pn of x. So log 1 over Pn of x. Okay, now I want to use the Varopoulos inequality. So I gave handouts to some of you with the proof of that. It really just takes a page. But it's a general inequality which, in this setup, it gives Pnx less than e to the minus the distance squared to x. So that's x squared over 2n times 2. This is the Varopoulos inequality. And in fact, this is, in this form, it's true for any Markov chain if the stationary measure is uniform, and with a small variation, it works for any reversible Markov chain with a small change. Reversibility is important. So then one can apply it here, and the key to get the short proof, this is summing over x, is we want to use Varopoulos but only on one term, only on this one, right? So, right, because log 1 over Pn of x is going to be at least, well, log half my plus x squared over 2n. So, okay, so plugging that in, we'll get, so this is at least sum over x, Pn of x, times a log half plus x squared over 2n. But then we just have to see what this means. If we move the log half to the other side, so we get log 2 plus h of xn is greater, what we have left is just the second moment of the walk, so expectation of xn squared normalized by 2n. Okay, and let's divide both things by n, so 2n squared, and use Cauchy-Schwarz. So this is bigger than the expectation of the walk, quantity squared over 2n squared. And you see immediately that if the entropy is sublinear, if this limit is 0, then the speed is 0. For the converse, we have to use a fact about relative entropy. That so this is one direction. Speed, well, entropy equals 0 implies speed equals 0. On the other hand, define a measure q. So q of x. Well, q is going to be uniformly spread over spheres. So q of x will be 2 to the minus k minus 1 over sk for x in the sphere of radius k. So the sphere is just all the points y with distance k from the origin. Okay, observe that this is a probability measure because the total measure of every sphere is like this. So when we sum these up, we're going to get a half plus a quarter plus an eighth, so we'll get 1. So this is a probability measure. And the basic relative entropy inequality tells us that 0 is at most, right? 0 is at most the sum over x of a Pn of x log Pn of x over Q of x. This is also not working. Okay, and what can we say about this? So so you see here log 1 over Q of x is certainly less than, well, log of a 2d to the power, or 2 to the power k plus 1. So I'm going to use d for the number of generators. Okay? So the size of the sphere is certainly, at most d to the k. All right? So we have that. So plugging that in here, we'll get here the sum over x, Pn of x, and the log will give us x plus 1. And then we'll get minus h of xn. Right? Because when we take Pn log Pn will give us minus the entropy. Okay, so what you have here is just the expectation of xn plus 1. And let's see, did I miss anything? So minus the entropy. So yeah, I missed the log to d factor. Okay, but that's all we need. So that shows us that it bounds the expected, it bounds the entropy from above using the expected distance. So now divide by n, pass to the limit, and you see that that if the speed is 0, then the entropy is 0. So it's the opposite of the inequality we got there. Slightly different constants. Okay, so that's the classical theorem. And then, so going to the next question is, so we know when there are bounded harmonic functions that are non-constant and when they are not. But when there are, what are they? How can they be described? So this is equivalent to describing what are the tail events for the walk. Now, one easy case is the tree. So there, the tail of the walk can be described by what is the infinite ray that the walk converges to. And that's quite classical and elementary to verify that this. So all harmonic functions can be represented as the expected value of some function on the boundary, when the boundary of the tree corresponds to the infinite rays. So at the time we won't go through this, but the Kaimanovich-Vershik question or conjecture concerned, so in their 1983 paper, they asked, so what are the bounded harmonic functions on the groups GD for d greater or equal 3. So as we discussed, for d equals 1, 2, the speed is 0, so there are no bounded harmonic functions except the constants. The question becomes interesting in d at least 3, and they identified a class of harmonic functions, and they asked if that's all of them. So, well, this class is determined by the asymptotic configuration of the lamps. So if I take any vertex and look at the lamps there, the vertex will only be visited finitely many times because the walk is transient. So the lamp will have an eventual setting. It will be on or off, and this is random, but we can ask, u of x to be the probability starting from x that a particular lamp, say a lamp at some other vertex w, is on. Okay, so this is a function of x. Okay, so, and I should say, so x is in the Lamplighter group, and w is a vertex in the lattice here, in ZD. So we start at the configuration x. So we have some lamps, in particular, the lamp at w could be on or off, and the marker could be somewhere. And we ask for what this probability, and this lamp at w is on, and here I mean at time infinity. So after the walk has traveled to infinity. So initially, we know the lamp is on or off at the configuration x. But what is this at infinity? Of course, it varies from one x to another. So if, in particular, in x, the marker is very far from w, then it all depends on what is the lamp at w in time 0 at x. But if the marker is, say, at w, then it's very likely that, or it's reasonably likely that the lamp will be flipped. This is a non-constant harmonic function, and more generally, you could do any function of the final states of lamps. So we look at the final lamps. At time infinity, we have some configuration of lamps. The marker has disappeared. And we can look at this kind of function. And we can ask, is this? So these are all harmonic functions. Very easy to check. Are these all? No. No, not just for finite set. So for any, because as in any, So I can. So if I have an infinite set, I will have to ask. I can't determine. Is this lamp on? Is this lamp off? And so on. But I can ask for an event involving infinitely many lamps. And such an event. So I can ask if. So any measurable. So the eventual lamps are a collection of. Although at finite time, only finitely lamps will be on. In the limit, when the particle has gone off to infinity, it will leave a trail of infinitely many lamps that are on. So I have a configuration of bits on the whole lattice, of which infinitely many will be on. And I can take any function, any measurable function of the bounded measurable function of this bit configuration, and take its expectation, and all of these yield harmonic functions. And the question is that it? Or equivalently, is the tail sigma field for the walk generated by the final lamps? This was the Kaimanovich-Vershik 83 conjecture, and it was, so I spent some months on it in the 90s, didn't work. Then in Anna Erschler, it appeared in 2011, but she did the work in 2005, showed that, So the answer is yes, these are all the harmonic functions, but for d greater or equal 5. And then the new result is that it's true for dimension at least 3, and the dimensions 3 and 4 are really the most delicate. So let me explain where this comes from. So the key is extension by Kaimanovich of this entropy criterion. So here is basically a Kaimanovich criterion. So suppose F is some sigma field contained in the tail and invariant under the group. So if an event is in there and you shift it, it's still in F. So for instance, the final configuration of the lamps, all events measurable with respect to that is such a sigma field. We know that's in the tail, and we want to determine, is it the whole tail? So he gives an entropy criterion. So F equals the tail, again, almost surely, so modulo sets of measure 0. If and only if you take the entropy of the walk given F, and this is sublinear. Okay? So just like we saw that the tail is trivial if the entropy of xn is sublinear. So what he says is if you have some candidate subsigma field, condition on that subsigma field, look at that conditional entropy and see is that sublinear or not. If it is, then actually F equals the tail. Okay, so it's in natural generalization. The proof is very similar to what I showed you. So I'm not going to go through it. So this is an abstract criterion. The problem is, how to apply it. So how did Anna apply it in dimension 5? Let me also say that there's also the fact that if you take the probability Pn of xn but given f, this actually always converges to so if you take 1 over n, the log of this converges almost surely to this limit of the normalized entropy. So that's just a technical point you can ignore. So the point is, in order to establish that f equals to the tail, how do you apply this criterion? So idea is find a set Dn, which is a deterministic set, so not a random set. Well, I should say, so I shouldn't say deterministic. So Dn should be it's not exactly deterministic, it's a deterministic function of our candidate, so of f. So it's a set it is determined by f, so that the probability of xn in Dn is large, say tends to 1. Tends to 1, and it's enough that this probability is just uniformly positive, and Dn is sub-exponential. So e to the little o of n. Okay, and that guarantees that the entropy, the conditional entropy is 0. Okay? So we want to find a set. So we want to be able to, given our candidate f, to predict where the walk is, and the number of possibilities should be sub-exponential. So how does Anna apply this? Anna Erschler applied this as follows. So we want to describe the set Dn. So we want to first know where the marker is. So for the marker, well, there are less than n to the d possibilities, right? Because the marker is somewhere in the lattice at most distance n from the origin, so we can be generous at most n to the d possibilities. So let's just enumerate over these possibilities. N to the d is a factor we can easily lose. So suppose we know where the marker is. Okay, then her idea is let's take a ball around the marker of radius n to the epsilon. Epsilon is just going to be small, it won't matter exactly. And let's enumerate over all the possible settings of the lamps. So we want to understand what is xn. Xn is a configuration at time n. And we see the final configuration of the lamps. So we have some uncertainty near the marker. So let's enumerate. We have this factor n to the d. Let's enumerate over all possible settings of the lamps in this ball. So that's still something we can afford. Now what about the other lamps? Well, there are lamps, the intuition is there are lamps before and after the ball. And those before should all be in their final setting because we're not going back there. And those after should be in their zero setting because we haven't gotten there yet. Okay? So that's all true if we can tell what's the before and after. So and in dimension 5 and higher, we can tell, because once we have the separation of n to the epsilon, basic properties of random walk tell us that the probability that this random walk will intersect with, so this is the origin where we started, and this time separation is enough so that the probability that this random walk will intersect here is going to 0. So that's all we need. So it's just, this is very standard estimates for random walk. And so that's it. So, well, almost it. So we don't actually see where, how do we tell this trail? Because we don't really see the walk. All we see are some lamps. Some are on, some are off. But the key is that these lamps are telling us where the walk is with only an error of log n. That is, if you take the lamps that are on and kind of look at the log n neighborhood of that, that's going to contain where the walk is, and by time n. And the key is not only, so I mentioned that the future of the walk and the past of the walk don't intersect, but there's something better. The same estimates tell you that they don't come within log n of each other. So it's really easy to separate what are the lamps from the past and the lamps from the future just by this log n separation. So we take the lamps that are on, look at the log n neighborhood of that, and that will have one component of the origin and then components, other components, which so those will be so the lamps before the ball will all be in the final setting. Yes.
Corridor leading to this ball of n to the epsilon too costly? When you have n, its length is n, and you're taking.
But we're not enumerating there.
So what are you doing in order to actually understand?
The corridor is just used to explain how we tell apart the past from the future. So because we don't see a connected path. We just see, occasional lamps that are on. There can be gaps between them, but the gaps are at most logarithmic. So if we look at the path from the origin with these logarithmic gaps, then all these lamps will be in the final setting, and then the lamps on the other side will be all in their off setting. So we can tell the past from the future. Now in the last 5 minutes, let me explain the new part. So all this is fine in dimension 5 and higher. In dimension 3 and 4, this argument fails because the future will come and intersect. If we have any separation like this, we cannot afford a separation here, which is order n. It has to be smaller than that, otherwise there are too many lamps in here. So the future will come back and intersect the past, and we'll kind of get a mess of lamps from the past and the future, and we can't tell which lamps should be off and which lamps should be in their final state. Okay, so how, and again, it's too many to enumerate over. So the key is to understand the combinatorial structure of these intersections. So although this will come to intersect, it can intersect many times, but not order n times. Because if I look at any individual point here in the past, the chance that it will be intersected by the future of the walk is not too high. It's like, it can be bounded by n to the minus epsilon over 2. So basically, it's just from the fact just from the fact that random walk, simple random walk in d dimensions, the fact that it will come back to the origin at time t is t to the minus d over 2. So the time it will, probability of returning to a vertex after more than t steps is going to be about t to the, so 1 minus d over 2. So if I want exactly t, I get t to the minus d over 2. If I want more than t, I get t to the 1 minus d over 2. So if d is, so this is, take d equals 3, so this would be 1 over root t. And that's the source of this, n to the minus epsilon over 2. So because we know we have a time separation of at least n to the epsilon, because between the past and the future here. So of these points, only n to the minus epsilon over 2 can be intersection points. Okay, but so how do we use that? We're going to enumerate over where these intersection points are. So remember, we have a factor n to the d for where the walker is. So that's not a problem. Let's take d equals 3. So n to the d is n cubed. Dimension 4 is just the same, even slightly easier than 3. So we have n cubed for where the walker is. We're still going to take epsilon less than 1 over d, so we can still enumerate over this ball n to the epsilon d over all the lamps in this ball. Now we're going to enumerate over where the future intersected the past. So how many options are that? Well, in the past, there are only n points, and the number of intersections is at most n to the 1 minus epsilon over 2. Okay, now actually there's some log factor here because I don't know exactly where the walk is. And so there are some logs, but they don't matter. So the point is, this binomial coefficient, again, you can ignore the log, it's still sub-exponential. Right? So it's, okay, so this is still sub-exponential as long as, so again, this log is not important. This, right, so you can bound it by n to this power. And that's still sub-exponential. So we can enumerate over where these intersections are. And in fact, when we take these intersections around any one of them, we draw a little, so we have this n to the 1 minus epsilon over 2 intersections. Around each one, we're going to draw a little ball of radius log squared. So we'll have maybe log to the 6n points. And we're going to enumerate over all the lamps in this little ball. So that will cost us 2 to this power, which we can still afford. So we've enumerated over where the intersections are and what are all the lamps near these intersections. Now what is left? What is left is still a lot of points. It's still linear number of points. And in these points, we have no hope of knowing which are the past and which are the future. They're kind of combined. But we can separate them into components. Because once we remove these little balls, right, so we have this number of little balls, n to the 1 minus epsilon over 2, corresponding to the intersections. They separated the past. Well, they separate this. So if we look at the component of the origin. That's some n points, order n points, that we want to separate it into future and past. So this component, each time you remove one of these balls, that component can break up into more components, but only to a logarithmic number, because this ball is logarithmic. So the total number of components after I take out all this ball is still about 2 to this number. Okay? And on each such component, it's pure. Either it's all future or it's all past. I don't know which, but whatever it is, it's not a mixture, because any mixture must come from the future and the past coming together, and already enumerated over that. So I look at all. So when I remove, so I have this jumble, which is before the ball, which is a combination of past and future. I don't know, but when I remove the balls of where the possible intersection is, I get components. They don't, and the number of components is just n to the 1 minus epsilon over 2 times some logarithmic factor. So I'm going to have another factor like this, n to the 1 minus epsilon over 2 times some power of log. But this comes from enumerating over the lamps in the little balls. This comes from, and this is really the new feature, that we're not enumerating over the exact lamps now, but just enumerating each of these big connected components. Are they past or future? And then they all get either 0 or the final setting of the lamps. So we still have just this number of possibilities. And all these factors multiplied together are still sub-exponential. So the Kaimanovich criterion holds.
So you can just say that you enumerate over the ordering at which you intersected this line, right? And this will dictate everything. It's just this factorial which you can take.
The ordering, but you have to use the fact.
And this will tell you which of these, this will tell you the partition and which are past and which are.
Oh, you start with past and future.
I mean, you have to use the fact that the number of intersections is small.
Yeah, of course. Yeah, you start with it. But
once you do that, it's just
a different reformulation of what you said at the end about the components. You have these. Okay.
Yes.
And so
Yes.
when there's a past component, right?
Yes.
So and then why don't you have to multiply with all the on and off options?
Because the past component, what it has, it just is going to get the final setting of the lamps, because the past component means we're not revisiting it. So the lamps at time n are going to be the same as the final lamps.
Okay.
Actually, I actually want to ask more questions. So, like for trees, like are these characterized as well? These functions?
Yeah, for trees, it's
Simple.
functions are. Yeah. It just as I said, it's just in terms of the rays. So infinite self-avoiding paths to the boundary, and the random walk will go to one of these infinite paths, and that characterizes the harmonic function is just given by functions on this kind of boundary. That goes back to 1960.
Like, and is there more general conjectures for a given Cayley graph? Like, what are these functions if it has something?
So there are conjectures for various classes of matrix groups. There are many open problems. If you go, instead of bounded harmonic functions, you go to positive harmonic functions. That's a much harder topic. So we don't know what they are on these Lamplighter groups.
You can do everything, just take Lamplighter over any graph which is transitive.
Yes.
So
Yes.
you think there is no abstract argument that any transitive graph.
There's no abstract, but there is.
You believe that it will be true?
No, it follows now. So Anna's argument works for all transitive graphs that have growth bigger than 5. So it's not just I explained it for ZD for D greater equal 5, but we know enough about groups to see that this is true, and about green functions on groups, that her argument works the moment the growth is bigger than 5. So the only open things were when the growth is 3 and 4, and those are very few options. And it's basically lattices, Heisenberg group, and finite extensions of them. And in all of these, the random walk estimates we are using hold. So basically, these were the only cases needed to understand the case of any group or transitive graph.
Okay, let's thank you, Val.